In this video, I will demonstrate how to solve partial differential equations using Laplace transform. We consider this wave equation. This is a wave equation for a semi-infinite stream because x is greater than 0 and t is also greater than 0. Now, this is the initial condition. ux0 is the initial displacement, and utx0 is the initial velocity. Okay, then this is the boundary condition at the endpoint x equal to 0. This is a Newman type boundary condition, and we also want to find the regions where the on the xt plane where u is 0. Okay, so how to solve this problem? So because the condition is when t equal to 0, we have the 0 condition. Therefore, we should apply the Laplace transform with respect to t. Suppose capital U is the Laplace transform of our unknown function small u with respect to t. Then we can apply the Laplace transform to both sides of the equation. Both sides of the equation here. Then the left hand side utt, after applying the Laplace transform by the property of Laplace transform, the left hand side becomes s squared capital U minus s small u x0 minus ut x0. So because our initial condition is that when t equal to 0, small u and the derivative of small u with respect to the time t is 0. Therefore, these two terms are actually 0. This is why we apply the Laplace transform with respect to t. Those interested students can try to apply Laplace transform with respect to x for comparison. Anyway, the best choice for this problem is to apply the transform with respect to t. Now this is the left hand side. Well, for the right hand side, uxx, we know that Laplace transform acting on uxx equals capital Uxx. Okay, we already mentioned this in our lecture. Therefore, the PDE after Laplace transform become this ODE. Okay. Now, as I said before, because ux0 is 0, utx0 is also 0, therefore we have for uxx equals s squared u, then this is an ODE whose independent variable, unknown function, is capital U, and the independent variable is x, and the s here should be treated as a parameter. Actually, this is a family of ODE. Anyway, we have this ODE after applying Laplace transform. Now, this ODE is easy to solve. The general solution is C1 as e to the exponential plus C2 times another exponential. Note that, as I said before, the s here is a parameter, so the independent variable is x. So the so this ODE is a linear constant coefficient ODE. So you can write down its general solution. Of course, the constant C1 and C2 depends on s, okay, on the parameter s. And for these two exponential function, the variable is x. The s here are just parameters. Okay. Now, but our solution, small u, we want to find a bounded solution. So since u is bounded, small u is bounded, this implies that capital U is also bounded. Why this is true? Because capital U x s equals e to the minus s t small u x t dt. If you take the absolute value, this will not greater than absolute value of u, because exponential is always non-negative. This will not greater than the bound of small u times this integral. Okay, but this integral is converged for s greater than 0. Therefore, this is bounded by another constant. This constant does not depend on on x. Okay, this constant does not depend on x. So this means that capital U is bounded as a function of x. So this forces C1 to be 0. Okay, this forces C1 to be 0. C1 must be 0. C1 is 0. Otherwise, if C1 is not 0, then this term is unbounded, contradicting which our argument on the board. So C1 is 0. Therefore, the general solution capital U becomes we only have C2. The capital U xs is C2s exponential minus sx over 2. Okay. Now we apply. We consider the boundary condition. Our boundary condition x equal to 0 is this boundary condition. We apply the Laplace transform to both sides of this boundary condition. We will have Laplace transform of this function 1 plus t square equals Laplace transform of u of small u x0t, which is just capital U x0s. Okay, but the left hand side we denote the left hand side by capital Fs. Okay, so after applying Laplace transform to the boundary condition, apply Laplace transform to this boundary condition here, we obtain I will obtain this capital Fs. As I explained previously, capital Fs is precisely the Laplace transform of 3 over 1 plus t square, but this is just the Laplace transform of ux0t, which is capital Ux0s. Okay, so we have an using this result, using the expression for capital U here, you can take the derivative of capital U with respect to x and then let x equal to 0. So you can see that capital Ux0s is precisely minus sc2 divided by 2. Okay, that is easy. Let me compute this here. So by the expression for capital U here, we see that x equals, okay, this is easy. I will not do this. Quite easy. Okay, so from this equation we can solve C2. C2 is minus 2 capital F divided by S, and then using this, having obtained C2, we can write the explicit expression for our capital U here. Now here we need to compute here we have the Laplace transform of 3 over 1 plus t square. Maybe you could not find the result of this Laplace transform, but actually we don't need to compute this Laplace transform explicitly, because eventually we will apply the inverse transform to the Laplace transform of 3 over 1 plus t square. Okay, that is with inverse transform applying to capital F. This gives us 3 over 1 plus t square. So we don't need to compute. We don't need to compute this Laplace transform. We simply denote it by capital Fs. Okay, this is a point in this problem. Now, having obtained this capital U, the Laplace transform of our unknown function small u, we applied the inverse transform. We will apply the inverse transform to capital U to obtain our small u. But before that, we need to compute the Laplace inverse transform of capital F, and also from the table of Laplace transform, you can find the Laplace inverse transform of this function, exponential divided by S. And also we have a Laplace transform of our capital F here. Okay, this is just 3 divided by 1 plus t squared. So the Laplace transform of the exponential divided by s is given by the Heaven-set function h t minus x over 2. This can be checked from the table of the Laplace transform. Here h is what? H is the function. Ht is 1 when t is non-negative and 0 when t is negative. So therefore, the ht minus is 1 if t minus half of x is non-negative. In other words, if t is greater than half of x, if t is smaller than half of x. Okay, that is the definition of this Heaven-set function. The original definition is here. Okay, but substituting the variable, the argument by t minus half of x, you obtain this expression. Okay, that is our Heaven-set function. That is the Laplace inverse transform of this function. Okay, we will use this. Therefore, we apply the inverse transform to capital U, as I said before, to obtain our small u, the unknown function, the solution of our PDE problem. Then our Laplace transform has a very useful property. The Laplace inverse transform of two functions equals the convolution of their transform. We apply this property. Now, because our capital U, go to our problem. Our capital U is the multiple of this function and the capital F. So this equals yes, here Laplace transform, inverse transform acting on this and also acting on F. Okay, the result is their convolution, as I read here. And the minus 2, because Laplace inverse transform is linear, therefore the coefficient, the 2 in front of F here, the 2 here and the minus sign can move out of everything at the beginning of this result. Okay, now substituting the result of the inverse transform of both factor we present here. Okay, you see that this equals that is the this part is the inverse transform of capital F. Okay, so you see we don't know what is the Laplace transform of 3 over 1 plus t squared, but we simply denote it by capital F. We don't know the expression of capital F. That is not a problem, because eventually we will apply the inverse transform to capital F, and then we go back to the 3 divided 1 plus t squared. Okay, then we convolution with the inverse transform of the exponential divided by s, which is just the Heaven-set function at this. Okay, at this argument t minus half of x. Then by the definition of a convolution, this gives us minus 6. We can move the 3. No, nothing. 3 and the minus 2 here give us minus 6. Then the convolution of 1 over 1 plus t squared and the h, by the definition of convolution, this is just this integral. Okay, then so this is the solution of our PDE problem. Let's go to the next page. For this reason, I will copy the result of our small u here, given by the last line, to the next page. Now, that is here. So, since the Heaven-set function h is, although this is a very easy function, easy to understand, but we try to compute the integral. Okay, so so we consider because the integrand involving h tau minus half of x. Okay, so we can see the case that t is less than a half of x and t is greater than half of x. So we draw a picture. This is the x-axis. This is the t-axis. So if t is less than a half of x, that is if this line is t equal half of x. So if t less than half of x, then the point xt is here. Then when t is when your point xt is here, you see that h for all t for all tau in this interval, for all tau between 0 and t, the tau will not greater than half of x. Therefore h tau minus half of x is 0. Okay, because your point x tau is here. So tau minus half of x is negative. Therefore, capital H, the value of capital H at tau minus half of x is 0. This means that the integrand, a factor of the integrand of the expression of u, of the integral expression of u is 0. So the integral is 0. Okay? So because this, for all tau between 0 and t, this capital H is 0. So the integral is 0. So we conclude that u is 0. Okay? That is to say, at this region, u is 0. Every point in this region, every point satisfying t less than half of x, our u is 0 here. Now we consider the other case that t is greater than half of x. So t is here now. So our point is here. Maybe I will draw another picture. Yes. So if t is greater than half of x, then given x here, your point t is greater. This is our point tx. This point satisfies t not less than half of x. Then our integral, go back to our expression for our solution. Our integral is taken from 0 to t. The integral is from 0 to t. So from 0 to t, let's look at this graph. Okay, from 0 to t, you see that your tau have two situations. When tau is here, then your point x tau is lying below the red line. Therefore, capital H is 0 here. Okay, h tau minus half of x is 0 here. That is for tau between 0 and half of x. Okay, maybe I should. Here is half of x. If your tau is less than half of x, then then tau is less than x minus half of x. Therefore, capital H is 0 there. Okay, as before. And if your tau is greater than half of x, but less than t, that is when your tau is here. When your tau is here, your point x tau is here. So at this point, x tau, since tau is greater than half of x, capital H at tau minus half of x is 1. Okay, so we know that our integral is from 0 to t. Our integral is from 0 to t, but the integral from 0 to t, can be written as the sum of two terms, 0 to half of x plus half of x to t. But when tau lies in 0 to half of x, the integral of this is 0 because h is 0 here. So this term is 0. So in other words, all the integral from 0 to t reduced to a single integral from half of x to t. Okay, so that is what I said. Our solution is the integral from 0 to t, but actually by the definition of h, this is only this equals to the integral from half of x to t. Okay, and of course this integral is computable. Okay, making a change of variable, changing variable, let u equal tau minus t. Then the integral is transformed into this integral, and the antiderivative of this function is arctangent. So the final result is 6 times arctangent half x minus t. Okay, so in conclusion, our solution is 0 when t less than half of x, and when t is not less than half of x, the u is 6 arctangent half of x minus t. So our solution, the graph of the solution is the reason xt, and our line here t equals half of x. So u is 0 here. For our solution, u is 0 here, and above the line t equal to half of x, u is 6 arctangent half of x minus t. That is our solution. Okay.